So, in this lecture, that is fourth lecture of fifth week, we will be discussing about application of physics of failure. I would not say application, but I would say potential of PoF for prognostics and health management. PoF as such, it works in tandem or standalone mode as part of PHM. This lecture will be bringing in more clarity. And remaining part, that is canary. Canary is also using physics of failure approaches for its implementation. So there also we'll discuss. So fourth and fifth lecture, fourth lecture is for PoF for PHM, and the fifth lecture is canary for PHM. So these two lectures together, it will complete the subject that we are discussing. So let us see electronic component. If we have an overview, we used to have the wall-based system, which used to be very bulky. Of course, in those days, that itself was all our transistor radios. They were built around that. Then came in the solid-state system, and before that, it was a relay-based system to create the logics and all that. And then we after a solid-state system, we got the digital systems, and digital system, that means hardware software combination, providing the solutions that happened. So now the PHM, the extension of PoF PHM has got benefits, because the software based system itself, like AI/ML, they made it possible to develop RUL algorithm even as part of PoF or as a data driven approach. So they became, so software itself became the enabler, which were part of digital system earlier also. So but the limitation is, when we discuss the hardware electronic reliability, we are not considering the software which make electronics as a digital system. So software on both the side, its potential we are using as AI and ML tool, but failure can happen because of software as well as hardware. That we are not discussing. So in that sense, I am giving you the hint and all that, how software can induce the common cause element into the system, individual component into the failure into the system. But then a detailed discussion is required when we have digital system. We are treating digital system which have electronics as well as which have software. Without software, the electronics is not complete, because we are talking about microprocessor, microcontroller, microchips, and we are not talking about what is the RAM, random access memory, its configuration, its combination logic, how they are working. So this lecture will, again I would, as a boundary I will tell that it is talking about software, but as a utilization as AI/ML, but not what is the software which is there on the disk. Probably there can be a separate topic for this. So presently we are limiting ourselves to the electronic parts only, like transistor. But how transistor is processing the input and output, that we are not discussing. How a transistor makes the 5 to 6, 7 transistor, they make OR gate, NOR gate and all for logic processing. Yes, that is another topic that we have to. An integration of PoF and PHM could be a promising strategy for RUL. Yes, if PHM is the subject we are talking about, RUL is our end objective, and there we are using physics of failure as a complementary or supplementary approach, or as an independent approach also. Okay. So in electronic reliability, the available literature demonstrates that not only PoF but canary approach, even canary approach, we say there is a different mode, but canary probably I'll come to the last lecture when I go into detail. But here I'll tell you, quite a bit of canary approach also use physics of failure model. In the context of PHM, the scope of this lecture covers live consumption monitoring. So traditionally in physics of failure, we call live consumption monitoring. So if I see the complement of that, it is called remaining useful life. So we are getting same information, but the taxonomy is different. What we have in PHM, RUL, we have live consumption monitoring, and of course monitoring itself is one of the it's called LCM monitoring. It's a field actually. End result is live consumption monitoring means we are knowing at each point of time what is the life. So it is complementary to what is remaining useful life. Okay. So I thought all along we had discussion, we had statistics, we had failure, we had physics, but on what? That was a question. So I gave you one example of MOSFET that was there, and I tried to explain the individual concepts. But look at this. We have all the not all I would say, but most of the components that I thought should form part of this lecture because the subject should be known. So we have the register as a first component, and I think we can say that register is a very rugged component. Unless until very high current or voltage is passed through it and it is terminal burn, we don't see any problem. So we have the register here, it's a symbol here, and this color code, it will tell the rating and related information for this register. These are the terminal, input terminal and output terminal we have here. And its a symbol is like this. When we make the circuit, electronic circuit, we represent this symbol, and then the function is reducing current in the circuit. Okay. If you want downside, reduce current, like we do it, let's say simple case, our chargers, of course we don't do it directly through resistor, there are many devices, but if you want to reduce the current a little bit for some application down the line, then we put a resistance there actually, because what we get at the end input is 230 volt AC at home, and so that same thing we have to use it. If I want 5 volt, but I have to bother about the temperature goes up in the resistor, and all related parameter we have to see. So accordingly, resistor or some other component will also useful. It is a component in itself, and how it can be embedded onto the system, it is a different ball game altogether. But you think about it, if I have to create a resistor on the microchip, how we will do it? Reducing current in the circuit is a one function, and then in electrical or electronic circuit boards it is used. So we all know probably if first component, if we know in electrical circuit or electronic circuit, is a resistor, and it is simple, one wire having some resistance, and it reduces the current. Okay, and then we have capacitor. The capacitor have it could be like a flat the way it looks like, or it could be a cylindrical capacitor also. Like if I talk about the aluminum electrolytic capacitor, it is like a glass tumbler, a 500 megafarad certificate capacitor. It looks like a tumbler actually, and which has got its own construction feature, electrolyte, and then different component, and they also degrade. That is we can discuss separately on that topic itself, and it is represented. This is a symbol for a capacitor, and what it does basically is it stores electricity for short time. That means if I want a circuit to handle smoothing the electrical ripples and noise in the circuit, if you want to do, I will use capacitors actually, So these are the only some applications. There are many we use capacitors and all. Then we have inductor coil. Inductor or coil. It is nothing but one coil, like a heater coil. It is a coil. It is wound on some central element, and then its a symbol is here. It stores energy as magnetic field. So that means if the current is passed through the coil, it will generate a magnetic field. okay, and that magnetic field can be used for charging a device or any other way. So it stores energy as magnetic field used for cleaning signals. So what are the application? Filters to clean signals, frequency in radios, and then wireless, increasing or decreasing frequency in radios, and wireless phone charging. Okay, these are the application. And then we have transformer. We all know that transformer are used to, there are two transformers: step up transformer, step down transformer. Step up transformer, they take the voltage to higher voltage. But here you are seeing the figure that it is symbol for step down transformer. So it is step down transformer. It is reducing the voltage. Where it will be used? I have got one 230 volt power supply, and I want to my chargers. They use a transformer. Okay, so it will step down, and it will this signal will fed to the rest of the. So the step down will be to the extent of 230 volt to 5 volt. So transformers have their own functions, and then we have diode. Diode means the symbol is here, and then the typical diode. I have just given one figure actually. Typical diode looks like this: lead, inlet, and input and output, and then it stops the reverse current. Its construction feature, if you study, it allows current to flow. It's like what we have a non-return wall in a hydraulic line. Diode is in the electrical circuit. So current cannot pass like this. Current has to go in direction. Allows electricity to flow in one direction. Light emitting diode, it generates the light. Stabilizing voltage, it is used in a voltage stabilizer also. And protection in phone charger. So imagine if the current start flowing in reverse direction, then 5 volt device, so 230 volt is connected here, 5 volt connected. If the current becomes reverse, it may damage the device. Transistor, typically it has got 3 terminals, you can see here, and this is collector, base and emitter. So these are the 3 component: input, output and base. So they have different function. Probably when I showed you MOSFET, this function must have been clear. Maybe you can do more studies on the MOSFET, transistors and all that. Even simply you can go to a shop and buy all these components and do a construction analysis, because it's very important if you are talking about physics of failure on electronics actually. Switching and regulation signals, it is used for switching means on off, and regulation means controlling. So it can be used as an amplifier for increasing the signal. Okay, sends signal from low resistance to high resistance circuit, acts as a switching in electronics. So it can be used as a regulation, that is like amplifier. Amplifier amplifies the input signal to higher signal. So this is it can do, but it can be this particular base. If we apply a small voltage, it can control, it can switch off, it can regulate many functions. So you can say a high power circuit is interfacing with a low power circuit where the transistor is there, and it is doing the controlling function. What is the function of a valve in a normal pump to tank circuit? Is the function, that is switching function, stopping function, and on-off function. At the same time, regulation function also. Same source is coming, and if you want to reduce or increase the flow, here it is electric current. So it is analogous to what we have in our home, a pumping system where we stop the flow, we regulate the flow. The transistor is doing. Only difference is it is this particular thing is interfacing with a very high electrical circuit. So it brings this particular device, it brings the power system into control system era. This is a gate, you can say, transistor. Then integrated circuit. Integrated circuit means number of transistors built on a chip, and a chip typically looks like this, and it has got many terminals here, input, output, they can be used as input, output, or if it configured as input or output, accordingly it has to be used, and it is symbol is here. So many transistors in one chip, complex logic processing task can be done here. Okay, and like this type of chip, it might have something like ranging from 100 to 500 transistors, so that is the capacity that we have. And then many transistors in one chip, audio chip, graphic, processor, programming, that can be done using the microchip on the same board, more than one microchip, and you can have any application there. And this is the most important component, and probably if discovery of transistor has been used in a mega way, it is the microcontroller or microprocessor. It is there in all computers everywhere. You can say millions of transistors are sitting on this, and there, in fact, the tribute to this device is, it is considered as a brain of any electronic, electrical device, process control, memory, data. It can be used, this thing, and like simple, if I tell your control, or even a rocket system, or even if a system of a nuclear plant, it is operating on this processor, because it can accommodate logic, input, output, it can process the data, and it can control certain data. If I want certain process to be complicated, process to be controlled, a microprocessor can do it. And any complex function like controlling, this is simple in washing machine, but it can do for mega systems the complex jobs, So these are the basic component, I would say. There may be many more. In fact, metallization and solder, that which are very important from the point of view of reliability of electronics, I have not discussed here. Okay, so having seen this, it was just that I should introduce you. I will come back to the physics of failure model, because these are the components that we will be modeling in physics of failure. So it is better to get introduced with that. So now life consumption monitoring, that is RUL in short. If we use the word in PHM, life consumption monitoring, that means how it is degrading, or it is not degrading at all. So that we do in physics of failure. It is a critical mechanism, it is done for critical mechanism. LCM can be interpreted as a complementary notion of remaining useful life, that I mentioned in the lecture. Loading parameters, it could be environmental parameter, it could be operational parameter. Okay, so for life consumption monitoring, we have to have knowledge, data, and their behavior and their degradation in this system. And then, like it happens in data driven method, the role of sensor is also important in physics based. See, based on the identified loading parameters, appropriate sensor for monitoring of load parameter can be identified. If I am monitoring a parameter, that means I need a sensor there. The way I need in data driven circuit, I need to have a sensor there. Okay, sometimes on an electronic board, there are constraints, So if there is a constraint, there is some mechanism I want to understand, and that thing is depending on certain parameter like voltage, temperature, and all that. So I can monitor that through my sensors. So they are direct measurement or indirect measurement, which will handle the problem of constraints. If the position of the sensor in the system does not allow direct monitoring of the parameter or critical value, a load transformer may be developed that allows the measure and load condition to be converted to the load condition for the failure. So some additional arrangement we have to do for the situation where we have constraint, we cannot monitor the direct parameter, we have to do some circuit and something has to be made, so that we can indirect information we can have through some sensor on the board itself, and we can do that monitoring and fit into our life consumption monitoring regime. Now you see, cumulative damage approach, especially we say it is applicable in all the fields, but for fatigue fracture, it is because if a crack is developed and then this crack slowly develops, and when it reaches the critical crack length, then the 40 limit comes actually, Now, it comes in the number of cycles range, but actually physically if we see, the crack can go supercritical after that. So, one adequate margin is required, and we can say this is our 40 limit. That means so many number of cycles, and then sometimes it is related to years also. So, in so many years, 30 years, 40 years, whether we will reach our 40 limit, and it start building like it is a log scale. Initially it will be maintaining some part 20-25 years for most of the cases, of course. Sometimes there are catastrophic failure. We are not talking about catastrophic failure. So, here it goes, and here the catastrophic failure occurs actually at the end, So, time matrix. Here we are using time matrix. Sometimes it could be number of cycles also if you can monitor, and you can monitor the cycle and their time period on which it stays. So, that will be a complete information. So, then cumulative damage, a common approach for fatigue failure modeling and modes is the cumulative damage approach induced by one Paul Green. He introduced this approach and popularized by Miner. Okay. Now, matrix is the cumulative damage matrix defined as because now we are talking about cycles. If we are talking directly about cycle, so then 0 to 1, which is assumed to represent the state of the material degradation. Okay. Example, if you want to understand through one example, the material degradation could be physical crack and damage, which I have given you about that, and the damage index could be the length of the crack in a bonded structure divided by the overall bond length. So, when the crack opens fully, it goes to the critical, how long it takes and all, and that happens in a cyclic mode, So, either you take number of cycle or time to failure mode. Now, a cumulative damage approach we are continuing, and here it is called damage index. Now, damage index could be anything, increase in crack length, or it could be because cracks, if you see in mechanical material, it is developing in certain development, then the direction will change. So, there an optimization, online optimization is required, which is the most prominent direction and all, and which is a complex phenomena. But let us say in electronic circuit, we want the operational parameters should work smoothly. Okay, so current should flow, and here the advantage in electronic circuit is the current low voltage, high current, they can be measured actually if we have something, particularly if we are designing an experiment. Okay, and like mechanical system, always there is same thing applies to even electronic system also. Sometimes the crack develops and it becomes stabilized. It doesn't go further. So, we have to be very careful about it. It is not a linear relationship, or it is not a relationship which can be predicted in advance actually. So, the damage index is TI applied and time it is available. So, what are TI applied and all? Time under degradation condition is called I, time under degradation, and time we apply the load. And the time to failure under the degradation condition I. So, T available can be given as, so I think it should be D. So D index, that is degradation index, can be given by T applied, whatever applied load, actual load is available, and what is T is available actually. Time domain actually, damage to date, DTD. If the damage is accumulated linearly, okay, you see I am putting the word linearly, meaning that damage due to load level and application period is independent of the damage state prior to the loading period. The damage to date can simply be sum of the collected damages. So, whatever data we collected on increase in crack size or whatever, so that can give you damage to date. That means what kind of damage has happened that is again we are talking about life cycle loads, So what is lead as on today, that is available, though it is using correct word, direct word, that is damage to date actually, and then average damage rate. It is nothing but summation of T applied upon Ti level divided by Ti applied. We are normalizing this, and this is called average damage rate. Okay, because this particular parameter will be required, how much time it will take to reach the critical stage, or how much time we have for going to the next stage, and last is damage at failure. Damage at failure, that means our remaining useful life we are telling. If the damage level failure is defined to be damage to failure, then the remaining time. So damage to failure, if it is required, this damage to do that. So we are getting a and dividing by average damage rate. Then we have RUL, the time in terms of RUL. So we got this matrix for cumulative approach to damage assessment and modeling actually. So let us see the flowchart of life conservation approach. So loading data, first we have to collect, then failure models you have to work out. So whatever time is available, geometry, material, loading, so time available will be a function of geometry, material and loading. So that model will look like this. So failure model, you can see, we can pick up from there, apply the damage assessment can be done by DI, T applied by T, cumulative damage by summation of all this T applied and T available divided by T available, and remaining useful life we can provide by damage occurring the required for the failure and damage to date, and divided by the range that we have over there, rate of this thing, average rate that we have, and we get this thing. So this is a small flowchart which summing up everything for consumption monitoring. There are some special aspect of life consumption monitoring. Okay, and these are this time based approach loading features. So many loading in so many days or years or hours. So the failure model may have to time component, and the time based load must be processed to extract load feature needed by failure model. So this exchange of information from time based to cycle and all that is required, and that is basically driven by what you want to model, our failure model, what it wants that information. Example is also there. A fatigue model may only need the cycle strain range, okay, to predict the number of cycles to failure, and different strain ranges would be different to different cycles of failure. So what we are saying is, here we are limiting ourselves to the frequency domain. Okay. Now if it is a cycle count is there, if you want to do the facility to data processing for fatigue based failure, cycle count methods have been developed. There is one called rain flow counting model, one of the well known model. Probably we have to see, but for the sake of completeness I have taken over here rain counting model. It is not within the scope to go ahead with this one. This method was later codified in, and it is a part of a ASTM standard, American Society for Materials, testing and materials. Cycle counting and hold time. You see, time factor is coming here in this thing, and here we are trying to signify, understand the hold test or dwelling period, whatever you may call, and that effect we want to see. Hold time implication has been studied by Clough, was and the reference I have given here, you can have access to this paper. And so these are different specific requirements for life condition monitoring, and probably we'll have to decide well before you start the modeling and all, what model we want with the time based, frequency based, and in the frequency based dwelling time, dwelling time, if that is there, what parameters we take, geometric parameters we should take, physical parameter we should take, material parameter what we should take, and what are the available literature that supports our research. So this is what about life consumption monitoring. And then in nutshell, I would say that mode of life consumption monitoring implementation is very important. One of the inferences is that live consumption monitoring approach can be embedded into a system or performed outside of the system. Now, if in a system, how to do it? Canary is the example. If you do it outside the system, it can be done in a physics of failure mode, or some experiment can be done. Okay, real-time potential of LCM, when properly implemented, the live consumption monitoring approach can be quite effective in maintenance and logistic maintenance. You can see here. So healthy is 0 to 0.4 I have given here, attention 0.4 to 0.6, 0.6 to 0.8. And then failure in this region is expected actually. So if I have this information available, let's say I have designed a meter and I have put it in the control room, or next to the system I am monitoring. Then I got the information for health. That means there is attention is required and there is a threat component. Probably as a conservative principle, I will start acting here, and before the failure domain comes, I start my action maintenance management and all that. Then RUL and maintenance management. So probably this is one kind of RUL indication that remaining useful life is up to here. Let us say if I am conservative, or I can take 0.8 also, and accordingly I can initiate the maintenance action. So in this lecture we saw role and capability of PHM, PoF for PHM, life consumption model, cumulative damage models we saw, and life consumption approach and monitoring of LCA. Next lecture will be on canary as its applicability for PHM.